For those of you who attended the workshop yesterday, welcome back. For those of you who are new today, welcome to the workshop. Today is day 2 of the Chemical Toxicants in Water, a GeoHealth perspective in the context of climate change. And before we get started, I'd just like to reiterate some of the ground rules that Kathy, Dr. Proper talked about yesterday. I'm going to give a brief introduction to today's speakers. Then each speaker will have approximately 25 minutes to give their presentation, after which there'll be a time for a question or two. During the question and answer period, either use chat, and I'll keep my eye on the chat, or just do a shout out. That's okay. That way I'll know that you're there. After we have our 3 speakers, we'll take a short break. Then we're going to go into breakout rooms. If you were involved yesterday, the breakout rooms, I think we all of the organizers thought were very successful. We'll go into breakout rooms. We'll talk about what we've heard thus far this morning, and then also talk about next steps and potential policy or remediation actions that might potentially be profitable moving forward. Then we'll reconvene as a large group, and then we'll chat for a while in a large group, talk about next some of the big questions, and then we'll move on to Wednesday's session. Speaking of Wednesday's session, there were scheduled 3 speakers were scheduled for tomorrow. However, Dr. Antar Jutla has run into a series of bad events, some of which are COVID related, unfortunately, and he will not be able to give his presentation tomorrow. Consequently, there will be 2 rather than 3 presentations, and those presentations are going to move up. So we'll start at the same time, and we'll start with the second presentation and the third, and have an abbreviated day for day 3. So we're sorry about that, but it was a personal issues that couldn't be remediated at this time. But before I begin, I'd like to say a couple of other brief things. Again, I'd like to do a shout out and give special thanks to the Arizona Biomedical Research Commission, the Arizona Department of Health Services, and specifically Drs. Baldwin and Bob Trotter, who have been more than generous in their support of this program. I'd also like to just mention the Center for Health Equity Research at Northern Arizona University, the Idaho Water Resources Research Institute up here in sunny Moscow, Idaho, where today it's only about 40 degrees outside, the Department of Civil and Environmental Engineering at the University of Nebraska-Lincoln, and the College of Public Health through the University of Nebraska Medical Center in Omaha, Nebraska. I'd like to thank all of our speakers, and of course, I'd like to give a special shout out to the CHER team, the IT team, which would be Amy, Marcel, Lisa, and Aaron. I thought they did a fantastic job yesterday, and the breakout sessions worked great and came back together wonderfully. So everything was great. I'd like to end up my little time here by kind of getting back to what Kathy was talking about yesterday and the ancient mariner. And the only point I want to make here is that I don't know how ancient the ancient mariner was. Maybe it's thousands of years, maybe hundreds of years. However, analytic chemistry obviously does not go back that far. So really, there were, in the day of the ancient mariner, there were no chemists. There were, however, as we all know, alchemists. And when the alchemists thought about the natural world, the way the alchemists thought was in this perspective, right? And here are the symbols, right? They really thought that there were 4 basic humors within the natural world: fire, water, earth, and air. Now, the scientists of the alchemists, the scientists of the time, also, in addition to these broad, generalized, environmentally partitioned partitions of the environment, they also had about 20 elements that they knew, and that they knew definitively. And one of them was arsenic. And arsenic, therefore, in a conversation such as we're having relative to chemical toxicants and water and health, it makes total sense. Arsenic is one of the first, and indeed one of the most ancient nemesis of humanity relative to drinking water systems. So I think it's appropriate today that we spend some time, the next three seminar speakers specifically, that we spend some time and we talk about arsenic, and arsenic specifically in groundwater. So with that, today, I'd just like to introduce briefly today's speakers, Dr. Alexander Van Geen, Dr. Melissa Lombard, and Dr. Janie Ingram, who will all be talking about different variants on this same theme of arsenic. And with that, I am going to de-share my screen. And Lex, you are welcome to share your screen. And with that, it's my great pleasure to introduce our first speaker, Dr. Lex Van Geen, whose talk is entitled Ending Toxic Exposure from Well Water in Bangladesh. Lex?
Can you all see my screen okay? All right, good. So I thought it was, we had a good discussion. There were interesting presentations yesterday and a great discussion. You will notice that a number of the themes we covered are in this outline for today's presentation that I'll be giving. And Amy can testify to the fact that I didn't change it. This is still the same thing that I sent to her over the weekend. So I'm very excited to be here with you and look forward to further discussion. I'm going to discuss one thing in the context of well water and arsenic in Bangladesh, and that is spatial heterogeneity. And you'll see how, you can probably already see how that then rather quickly leads into a discussion of field kits. I will describe an enormous program that the government of Bangladesh has launched to test between 5 and 10 million wells for arsenic in the coming months. I'll describe to you how this, we hope to be able to carry out a collaboration that we have with the government to make this information available through smartphones. Obviously very useful not only for collecting data, but also for accessing data. And a randomized control trial to actually quantify the effect of using this sort of technology. And then I'll switch to the other topic, which we touched upon yesterday as well, with a number of presentations and comments, and that's how we could sort of spread the word, that it is important to test your well and respond to it. And therefore, I'll say a few things about science education. For context, let me first show you a map of Bangladesh, a country of over 160 million people, average population density on the order of 1,000 people per square kilometer. So perhaps a little rather different from the situation that many of you experience on a daily basis in the Midwest. But it is largely a rural country and without much of a public water system, supply system, piped water, anywhere beyond the main cities. And so this map is based on testing that was conducted with a field kit between 2000 and 2005 of about 5 million wells throughout the country. And the color coding shows you the proportion of wells at the level of the union, of which there are about 5,000 in the country. So the proportional wells relative to what is still today the standard for drinking water in Bangladesh of 50 ppb arsenic. And what you can see there is tremendous spatial variability. Clearly, some parts of the country much more affected than others. So the southern part in particular being highly affected. But even in those red zones, often, if you are at 80, 85, 90% of the wells being above 50 ppb, there's still a significant number of wells that are low in arsenic. And I'll come back to that in the context of spatial heterogeneity as well as mitigation. So that's for background. The other chart on this page shows you the evolution of, in blue line, is the growth of the rural population of Bangladesh. And you can see that it essentially has plateaued at about 100 million 20 years ago. People are still born, but often they move to the main cities for economic reasons very often. At the same time, what the dashed line shows is our way of estimating the total number of wells in the country, and it has continued to grow. And so whereas around 2000 on average 11 people in our study area, we'll zoom in on that in a minute, 11 people were drinking from a single hand pumped tube well. This has essentially been reduced to about 5 to 6 people. So every household, rural household, has its own well today. And then there are various test programs that I'm showing here. The BAMWASP is the acronym for the Bangladesh Arsenic Mitigation and Water Supply Program. That is what led to this rather spectacular map here on the left. Finally, at the bottom here, what I'm showing you, what the best estimates were of the population exposed to more than 10 ppb arsenic, which is the World Health Organization guideline for arsenic in drinking water. I can tell you that in the Netherlands, water utilities are now have volunteered to reduce the arsenic content of their distributed water to 1 ppb because of health concerns. And so states like New Jersey have already lowered it to 5 ppb. I wouldn't be surprised if there were further reductions in that standard in the coming years because of the health effects that are increasingly apparent from low exposure. So we're not talking about arsenic poisoning, on the spot. We're talking about chronic exposure to arsenic from drinking water. And so what you see is that number of people exposed was about 60 million 2 decades ago. It has gone down, but it's still at over 30 million people. And something needs to be done and that's one of the factors that has driven the government to conduct yet another national testing campaign. This is just a depth section. I made a random draw of 10,000 out of these 5 million wells, and I'm plotting them here as a function of depth. And so we are covering here the upper 300 meters. This is a largely unconsolidated material, aquifer draining the Himalayas, an enormous supply of sediment, and this delta floodplain environment, which keeps growing towards the sea. The y-axis on this plot has no meaning. That's just a random number, if you will. But what you can see here is the distribution of arsenic in these wells. So red refers to, in this case, more than 50 ppb, blue between 11 and 50, so between the WHO guideline and the country standard, and blue would be meeting the WHO guideline. And my point here is that the high arsenic wells are concentrated in the upper, say, 50, 70 meters of the aquifer. Deeper aquifers are typically low in arsenic. The density of the points, this was a random draw, reflects the fact that most of these wells less than 100 meters were installed privately, individual households. Most of the deeper wells were installed by the government or NGOs. And that, I think, is going to be an important factor for future mitigation. Most of the installations are done privately, and that's not going to change anytime soon. Zooming in on the box here on the yellow, which is a transition zone, you can see the red here in the lower right corner and the blue or white, which means there was no reason to test, in the upper left. That is where we started our work, meaning Columbia University, with the University of Dhaka and other local institutions. And we focused most of our work on a sub-district called Arai Hazar, which is outlined here in this rectangle. And you can see within this rectangle, again, the northern part, less than 20% of the wells are contaminated relative to 50 ppb, and we have some zones to the south with a much higher proportion, including a red zone here. So why did we pick this area? Well, the study was really launched through a grant from the Superfund research program. Might be surprising to some of you. Why should the Superfund support any research, epidemiological research in Bangladesh? It's because 20 years ago, there was a lot of discussion on whether the EPA standard should be lowered from 50 to 10 ppb. There was pushback, the Bush administration came in, and so people realized that essentially not enough was known about the health effects of arsenic in drinking water at the time. And so we were successfully able to argue then to start this study, which has lasted 20 years. In that format, it has ended now. The funding has not been renewed. These are sort of vintage pictures almost from 20 years ago. The overall Superfund project was led by Joe Graziano, a toxicologist at the School of Public Health. A key person was Habib Hassan, who was actually a cancer epidemiologist at Columbia University. He later on moved to the University of Chicago, but he had, of course, he was trained originally in Bangladesh and had a lot of local contacts. And then on the earth science side, Kazimatin Ahmed, a geology at the University of Dhaka, was a key person for us on the geosciences side. So this study was called Health Effects of Arsenic Longitudinal Study, with the acronym you can see. It started with, sort of my first task was to plan a sampling of 6,000 wells. No discussion of field kits at the time yet. They really weren't sensitive enough or accurate enough at the time. And based on that information collected in 2000, 2001, Habib Hassan's team recruited 12,000 adults of childbearing age, and we followed them essentially for the past 2 decades. Here are some pictures. This is what a hand pump tube well looks like, cast iron. It's unconsolidated material. It's sort of useful to know that a team of 3-4 men in this particular environment can install a 300-foot well within a single day without using any tools, using only PVC pipe and using the hand as essentially a check valve, a way of lifting the water, breaking up the sand and pumping it out. Another sort of vintage aspect at the time, we recruited this large cohort all with paper forms. There was no involvement of smartphones at the time. Feel free to ask me questions if there are any confusing points that I'm making. This is what the distribution of arsenic looks like at the time. When we started this study. Some broad outlines, which are you can gather that from the pie diagram. So more than half the wells contain more than 50 ppb arsenic. Some of them up to 1,000 ppb. So very high levels, 100 times the WHO guideline. Only a quarter of the wells met the WHO guideline, not surprisingly, in the northwestern portion of the study area. You remember the map I showed earlier. And so this is what we started with in 2000 and 2001. Many studies have been conducted. We, of course, delivered these results. The government conducted a testing campaign again in 2003 under BAMWASP. We did some more testing in 2011-12 and more recently in 2018. What I'm going to flip to now next is to show you exactly the same map, but showing you what the arsenic content is of the wells that people were drinking from as of 2018. And this is what it looks like today. So what you can see is that 2/3 of the wells now meet the WHO guideline. We still have about, an eighth of the wells with more than 50 ppb. There's still some tremendous spatial variability in the arsenic distributions in the villages where there are some red spots still, but overall an encouraging result. Now, we don't claim this represents what happened throughout the country. The rest of the country did not experience these multiple testing campaigns. We had also, most families in this area, there are about 75,000 people living in the study area. We've recruited 12,000. So most families have one person who is part of our study. That is, of course, a way of reinforcing the message. Arsenic, drinking high arsenic water is not good for you. But it is at least an indication of what is possible and what is still difficult in spite of this follow-up and this reinforcement. One thing I want to point out is that our most recent campaign was conducted entirely with locally recruited staff. So this is a team of 10 women who's tested in a previous campaign 50,000 wells over a year and a half, and they did a tremendous job. And a similar team conducted the testing that led to this map here. These are the field kit results. But what I'm going to show you next is probably the biggest intercalibration to date between field kit results, which were delivered on the spot to the households, and laboratory measurements by ICP-MS. So we have a total of almost 4,400 tests, both field kit and laboratory measurements. The kit we use is the ITS Econo Quick Kit. It's probably the cheapest on the market. When you buy it in bulk, it's about 30 cents per test. It comes with its strips, the bottles, the reagents. We don't use reagent 2 for any one of you who's interested in that. That's just an oxidant to oxidize sulfides. There's very little sulfide in these waters. And this is what the result strip looks like. So you have a strip. I should say the reaction is the good side method, which dates to the end of the 19th century. So there's no new chemistry here. I think what is new is the packaging, the quality of the reagents, and the price that this particular supplier was able to deliver these kits for. And so depending on how yellow this test strip becomes, it will tell you what the reading is. So you can see there's 1, 2, 3, 4, a little bit more than there are 1, 2, 3, 4, 5, 6, 7, 8, 9 different readings. And what we've done here is we bundled 0 and 10 ppb, 25 and 50, and then all the ones above 50 starting at 100. And what I'm comparing here is how these 4,400 samples distribute in this matrix. The upper row show you the ICP-MS results. And so what this table shows you is that of the results that the kit said contained up to 10 ppb, it turned out 2,647 indeed did, according to the ICP-MS. 122 were within the 10 to 50 ppb range, and only 5 actually contained more than 5 ppb. And similarly, in the other categories, so the diagonal is the largest number, and also in the last point. And so overall, what this tells us is that 91% of the results were correctly classified, and very few were incorrectly classified, in the sense that 0 to 10 should have been 50 over 50, and anything above 100 should have been less than 10. So so we have the 5 and the 7. So by and large, this was a remarkable performance of the kit, combined with the dedication of the team of women who did this work. So that is a sort of a discussion I still have with analytical chemists, and as I said yesterday, I think this settles the situation pretty well for the kits. Now, why did the exposure decline? I showed you the more red map, I showed you a blue map, not quite. Well, this close-up of a typical village gives you the answer to a large extent. Most of the decline essentially was based on this spatial variability. This is a village. You can see there's a scale, 159 meters here in the bottom left. And essentially, when I made that calculation in our early data, even though 50% of our population had a high arsenic well, it turns out that 90% lived within 100 meters. So a reasonable walking distance of another private well to fetch water from that could be low in arsenic, that would be low in arsenic. Now, of course, it doesn't always work. That's why the switching has never been total. Some wells are in rather public locations, like this one in the lower left. Others clearly at more private locations, next to the latrine or the bathroom or something like that. But the overall figure is this one. Between 50 and 60% of the people with a red dot switched to a well that was either green or blue, without doing anything else, without installing a well, but based on the testing. I think that's a really strong demonstration of the importance of information at the very local scale. Sorry. So that was the first reason. The other reason is I'm going to show you with maps and a cross section again. This is the original map, just in a slightly different format. And this is a section. Here the longitudes actually correspond. And you can see that this cloud of blue points here in the upper left are these somewhat deeper wells, deeper than 30 meters here. And so this has to do with the geology. Where do you have, for those of you who are geologically inclined, where do you have unperturbed Pleistocene sediment? Orange-colored, rust-colored sands, that's typically where you have these low arsenic wells. Well, what happened in 17 years is that the local population, based on the information we provided, based on very business-oriented drillers, local drillers who knew how to exploit this information, you can see that this cloud of blue point expanded dramatically. And so the second reason for the decline in exposure is that individual households made decisions, made investment, spent another $200 to install a deeper well. So those are the two reasons. Now, other things have happened. The government has installed some deep wells. Those were expensive. They didn't affect a similar fraction of the population. Some arsenic removal systems were tried. They were not popular and abandoned pretty quickly. One pipe water supply was installed, and it it helped several dozen households, but again, very expensive. The two most impactful actions were actually private initiative, sharing existing safe wells, and installing deeper wells that reach into these Pleistocene aquifers. All right, so I hope this adequately covers the first 2 points that I wanted to make. I've mentioned the government program, which is going to sweep through the whole country again, at least the affected half of the country, produce data. One piece, and it's, this is one call for bids from NGOs that are being hired to do the training and then track this information from the government. This is now one wrinkle is that they will use a different kit, not the one that seems to go pretty well. It's still based on the good site method. I'm not worried. It uses 100 mils instead of 50 mils. It should be more sensitive. That's why the strip here, the lowest reading would be 5 ppb. I think that's plausible. But this particular kit has never been commercialized, so it's a little scary to have 5 million wells being tested without much trial ahead of time. But that's the reality, even though I'm not worried. One piece of good news is that unlike the previous testing campaign, everything will be recorded with smartphones. And the only thing that we suggested to the government is that rather than having to enter 0.0005 and 0.050 and 0.5, there will be actually a pull down menu here instead of this box here where you have to enter the number. And I think that could reduce the number of errors from entering the data significantly. This is supposed to, well, obviously COVID slowed it down. It's supposed to happen in the coming 6 months. And it will be a fantastic data set, as you can see. Well, let me see how we're doing in terms of timing. I think I have time to briefly show you. So we've with our own data, so we have 50,000 well test data. We're going to, we've produced an app, and I'm going to run a very short video for to show you how that works, to deliver this information. So we have 50,000 data points in it. We hope to have 5 million eventually. Can you see the video screen here? Maybe someone can tell me.
You can see it.
Okay, and I'll be quiet because there's a bit of text.
The app is called Milk, which means too well in Banda. And Nadia Jamil here shows how to download it from the Play Store, install it on the smartphone, type in Para Hazar, which is our study area, and zooms in on an area, Dori Sachavanti, which is a village where we have conducted a number of studies. The close-up shows the distribution of high and low arsenic wells, and the yellow circle shows indicates the wells within 100 meters of the user. You can click on individual wells to verify their status, look at the test strip result, a high arsenic well here, and eventually this feature will show the photos of the actual wells. You can also click on the upper right of the screen and show wells that are deeper than 45 meters, here all low in arsenic. Finally, the screen at the bottom shows a site score, a priority score, if you will, for intervention, which here is 28, and 28 refers to the number of red wells within 100 meters of the user. The green marker shows the user walking in that village.
And so we recently received some funding from the USAID, to measure the impact of this app by conducting a randomized controlled trial. We will select 100 villages with the data. Half of them we will provide the information with the app, and of course encourage people to use it. The other we won't until after the study has been conducted. And then 6 months into the deployment of the app, we will conduct a response survey and say whether it's made a difference in terms of switching or installing deeper wells, or even expecting public wells to become more freely available to the public at large. All right, let me switch to the last topic here, which is education. So it turns out one of our PhD students, Khalid Khan, conducted a study in 14 elementary schools and involving 840 children, and they are located here. What the program entailed was training of teachers of these schools, the organization of drawing contests and the like, to explain to these children the risks of arsenic when drinking from high arsenic wells. And the idea, of course, is that they would convey this information back home. And the results of that were remarkable. It turns out that, and we tested wells, of course, and provided wells at schools where necessary. It turns out that among the control population, so the control schools, 40% of the households switched in response to the testing without the extra education. But this proportion doubled to 80% in the kids, in the families of the children who were going to the schools with the intervention. So we thought that was encouraging and gave us hope. But of course, we wouldn't expect children, elementary school children, to use the kit. I don't have a project yet involving high school students from Bangladesh. I have no reason to think that it should work, based on my experience with a kit we developed in our lab. Francisca Landes, a recent PhD graduate, conducted, and that was to screen the lead content of soil in Peruvian mining towns. Here they are doing a wonderful job mining the lead content of Cerro de Pasco using a kit. So I have no reasons to think that high schools couldn't do the arsenic testing as well. I'll conclude with a project that involved master's level students from a local college in a rather remote part of India, Madhya Pradesh, where we trained them to use a local field kit for fluoride in drinking water. And here you see them doing that. And they were actually from the villages that the testing campaign was conducted. By working on weekends, in their free time, they were able to map the fluoride content of these mostly government-installed wells in Madhya Pradesh. The yellow ones are the ones that don't meet the standard. You can see there's a bit of clustering. Most villages, fortunately, don't have a problem, but some of them do, and they've been identified. And I think this could set the stage for more educational programs based on testing. And I think it's a win-win. There's environmental information, health information, and that students learn about testing, about measurement, reproducibility, mapping, and things of that nature. And using my maps, you can make all this information very available. This is essentially what I had to tell you. Thank you very much.
Thanks, Lex. That was great. Not only was your talk really interesting, but I'd have to testify that this is one of the first times that I've seen someone use video and it came across flawlessly, which was both a testament to you and also to NAU and their IT that this all worked out. So that's wonderful. We just have time for one quick question, and there is a question on chat, so I'm going to ask the question from chat. And that is, were there examples in these communities where the wells actually went dry, which forced the community members to go to other wells? Did that play a part in the overall strategy?
So most of these wells are recharged every year, in the monsoon. So you do have a seasonal, especially if you have a lot of irrigation. The main draw of water are not these hand pumps, even if it's a densely populated area. It's the irrigation for rice cultivation. So they don't go dry. Where you have issues of dropping water levels, of cone of depression, is around the city of Dhaka because of the municipal water supply. There you've had the water drop by 70, 80 meters. And actually, so the deep aquifers have been affected by that all the way to our study area. So it is an issue because these are all suction-based systems. And as soon as you have to start pushing the water up, it becomes more expensive.
Great. Thanks, Lex. For the sake of keeping on schedule, we're going to move forward. And let me remind you all that Lex, as well as all of the other speakers, both today and yesterday and tomorrow, will be involved in the chat rooms. So if you are lucky enough to randomly draw a seat in the chat room with Lex, you'll be able to talk to him more during that time, during the breakout session. Also, we're all going to get together after the breakout session, so there'll be time to talk again to Lex and others at that point relative to further conversation. So with that, let's move on. And the second speaker in this triad of speakers this morning is Dr. Melissa Lombard. And she is speaking on today, geospatial models of arsenic in private wells to assess the impact of drought and support human health studies. Melissa?
Thank you. Thanks for having me. And let me share my screen. And hopefully, are you all seeing my PowerPoint?
We see it.
Yes, okay, great. So yes, I'm a hydrologist with the U.S. Geological Survey, and I'm in the New England Water Science Center in the New Hampshire office. And today I'm going to present to you results of a few recent studies that we've completed, primarily modeling studies of arsenic in private wells. One study looked at how drought might impact arsenic, and the other study was actually developing new models in collaboration with epidemiologists, and those models will be used in subsequent human health studies. So first, just to give some background. Oh, and I'm not. My slides are not moving forward.
I sometimes have that when I do it in PowerPoint instead of PDF.
Oh, here we go. Okay, yeah, that was weird. So just to start off with some background information. Many of you already know this, but why should we study arsenic in private wells? There are numerous documented impacts to human health, both from acute exposures and chronic long-term low-dose exposures. So as a result, in the US, the EPA has a drinking water standard of 10 ppb for public water supplies. Some states, New Jersey and New Hampshire, have lower drinking water standards of 5. But those are all just for public water supplies. So generally, the private wells are not regulated in the US, and water quality testing is a responsibility of the homeowner. I think, as we talked about a little bit yesterday, and I'm sure we'll discuss more today, informing homeowners that there is even the possibility of arsenic in their well, just to get the word out that they should test their well. That's a pretty big undertaking. And then, not everybody tests their well, not everybody's capable financially, and so, and then interpreting the results once the homeowner gets them back is a whole nother issue. So we really, as a whole, compared to public water supplies, who, they're required to test their wells on a regular, their water supplies on a regular basis. There's really a lot that we don't know, or we have to, there's a lot we don't know about where private wells may be high in arsenic, specifically at the more local levels. There is heterogeneity between locations, certainly, as Lex pointed out in his talk. So just one quick slide on arsenic geochemistry in groundwater. And this kind of gets, again, at, you can have two wells that are very close to each other, but have very different arsenic concentrations, and that can be due to they may be drilled in different aquifers, they may have different depths. So the redox, the amount of oxygen in the system, and the pH are very important in determining if arsenic is dissolved in the groundwater. And typically, arsenic occurs in slightly alkaline water with low oxygen. So this first study, it provides some, this was completed in 2017 by Joe Ayotte, a colleague of mine, and we work in the same office. And this was done in collaboration with the CDC and the USGS. So Joe developed a logistic regression model, which essentially you can think of as like a linear model for the whole US to predict the probability of arsenic greater than 10 ppb in private wells across the US. So the model was built using results from private wells only. And you can see the variability. The brightest red color is a greater than 50% probability of high arsenic. So this original model was constructed using over 20,000 well measurements. The different colors indicate the general range of arsenic concentration. So the black colors, black dots have quite low, less than 1. Light blue is between 1 and 10, and dark blue is greater than 10. So the final model that was developed contains 42 predictor variables, and they're all available. All the predictor variables are available as a GIS continuous layer, which then once that model equation is developed, it is applied to individual squares for the US to develop that final map that I showed you on the previous slide. So for example, the 30-year average annual precipitation was an important variable in this model. And so the most significant variables fell into a few groups. So the geologic indicators, so bedrock and superficial geology, either the presence or absence of that as a binary indicator. There are also geochemical data sets available for soil data across the US. So some of those were important. And then also hydrologic and meteorological variables. And so next, I'm going to talk about how we looked at the impact of drought on arsenic. And this we use this model to do that. And basically, that was possible because precipitation, average annual precipitation and average annual groundwater recharge were important variables in this model. And so this was a study that was recently completed and published in January of this year, basically looking at how drought might impact arsenic in private wells across the US using that previously developed model. And again, this was done in collaboration with the CDC and the USGS. So in order to assess this, I basically simulated drought conditions and systematically changed the values of average annual precipitation and average annual recharge in the model. So based on the original model equation, we anticipated that as you decreased precipitation, arsenic, the probability of high arsenic would increase. And as you decrease recharge, the probability of arsenic decreases. So there's an opposite effect here when you are in a drought. And so I did 8 different model run simulations, changing precip and recharge by different amounts. And the model behaved as expected when you decrease precip, arsenic overall over most of the area of the US increased, and when you decrease recharge, arsenic also decreased. This drought simulation run 7, where there was a 25% decrease in precip and a 50% decrease in recharge, was most similar to conditions experienced throughout the US in 2012, when a large portion of the country did experience drought. And so the change in the probability of high arsenic was mixed. It depended on the location, and I'll show you maps in the next few slides to illustrate that. So first are these illustrate if you just change one variable at a time. So on the left is precip, on the right is recharge, and the maps indicate the change in probability between normal conditions using 30-year average climate values for these variables. And so when there is a positive change in probability, that indicates there's a higher probability during drought conditions. So the darker purples indicate higher probability. So you can see that throughout most of the US, when you reduce precip, the probability increases, and then conversely, as you reduce recharge, the probability of arsenic decreases. And this is the map for the conditions that were most similar to those in 2012, with a 25% reduction in precipitation and 50% reduction in recharge. And the map shows that there is variability. So there was actually a decrease in probability, this light blue color, in the Pacific Northwest region. And then there were higher increases in the probability from 1 to 50% increases in the Midwest, Florida, and South Texas especially, and then some smaller locations in New England. So from the results of the arsenic models, and also this estimation of where the domestic well population is located in the US, this is a publication that came out in 2019, where we estimated the domestic well population for the years 2000 and 2010, that based on population density and where roads are located. This used to be information basically on the census up until 1990. There was a question about where you get your water from, and also if you have a septic system, but those were last on the census in 1990. So kind of extrapolating from data based on the 1990 census data out to the years 2000 and 2010, we were able to estimate where the domestic well population exists, how many people are on domestic wells. So taking the arsenic modeling results and basically multiplying them by the domestic well population for the US, you can get an estimate of approximately how many private well users might be using water with high arsenic. So under the average climate conditions, that number is estimated to be about 2.6 million people. And then during that drought simulation that was most similar to the conditions of 2012, that number actually increases to 4.1 million people. And if we looked at this by state populations and increases in population during drought, so Ohio, Indiana, and Florida had the largest estimated population increases. And that's both a function of that there are a lot of domestic well users in those states, as well as those states saw an increase in probability. When you look at it in terms of the largest percent of domestic well users, New Hampshire comes up to the top of that list. So approximately 8.2% of domestic well users would see an increase in arsenic during drought in New Hampshire. And so New Hampshire is a small state, we have a small population, but a large percentage of our population relies on domestic wells for their water supply. And then a second component of this was looking at the duration of drought and probability of high arsenic. So the map on the left shows the number of weeks of moderate drought or worse from the drought monitor during 2012, and these are based on county level data. And so taking the change in probability of high arsenic within the county based on the arsenic model and comparing it to the weeks that that county was experienced drought during 2012. The numbers across the top are the numbers of counties in each bin. Here we have the number of weeks in moderate drought or worse. You can see the median value tends to increase as the drought occurs over longer time periods. So some conclusions and limitations from that study. Overall, the model suggests that the probability of exceeding 10 micrograms per liter in domestic wells increases during drought. And then also the longer the duration of drought, that also tends to increase the probability of high arsenic. This was a national scale study and individual results may definitely vary at an individual well, and it does not step in or take the place of testing at individual wells, but it can give us an idea of what may be happening. Some potential next steps with this project would be to confirm or dispute the modeling results. I mean, it is a model. So to actually go out and get field measurements to see if what the models predict is actually occurring. We are currently working on a case study in Georgia comparing arsenic concentrations with date of sampling and what the drought conditions were at the time of sampling. Another interesting thing that would be possible is to use climate models to predict future scenarios. So I basically hindcasted back, but it would be interesting to see what climate models predict. Okay, so moving on, this study was just published in March of this year. We developed machine learning models to predict arsenic in private wells throughout the US. And so the previous model that was used in that drought study, the one that Joe Ayotte developed, was a logistic regression kind of, that was a statistical model. My mind is, but a more traditional statistical model. Here we use machine learning and developed 4 different models with input from epidemiologists. So this project was part of a Powell Center project. The Powell Center is within the USGS, and they promote projects where you bring together groups of scientists from 2 different disciplines, and they have data sets within their disciplines and try to use those data sets to come up with new and exciting science. So the models that I developed in this project predict arsenic, the probability of arsenic greater than 1, greater than 5, and greater than 10 micrograms per liter. And then we also developed a random forest classification model where the model predicts which category of arsenic you would be in. So basically low, medium, or high arsenic. And so this slide and the next just show the results from these models. So top left is arsenic greater than 1, and you can see there are large parts of the country where it is predicted to be. So here the bright red is greater than 70% probability of arsenic exceeding that threshold. And then arsenic greater than 5 is the map on the top right, and arsenic greater than 10. And in general, the results for this map are consistent with the results from the previous modeling study. And then this is, these are the maps from the random forest classification model. And this one might look scary, but the one on the top left, it's the probability of being less than 5. So across most of the US, large parts have a high probability of being less than 5. And then this map in the bottom right basically just gives the category that pixel is most likely to occur in. And there are Texas, the basin and range area, relatively large areas where the model predicts arsenic greater than 10. This is another study that was recently published by a graduate student at Columbia University. She looked at comparing private well water, so the results from the machine learning models, to data they had assembled from the EPA on community water supply arsenic concentrations across the US. And so the main takeaways from this paper are that there were positive associations between the private well water modeled values and the community water supply concentrations. Those associations differed by region within the US, and also community water supply sources. So of course, many community water supplies use surface water, and they tend to have, and they may mix with groundwater. So Maya did take that into consideration. And then also she looked at sociodemographic attributes of the water supply area. And the associations between the public water supply and private water did decline after the final arsenic rule implementation. So the public water supply arsenic values were available for before the reduction in the arsenic standard from 50 to 10, and then after the implementation of the lower standard. And so the association between private well water and public well water was less after the implementation of that rule, kind of implying that the rule is working and the public water supplies are, for the most part, getting rid of the arsenic in the water. Some ongoing collaborative projects that are, I think these are all between, well, no, not the last couple aren't, but most of these are between USGS scientists and epidemiologists. So the first two are using the results from the machine learning models to compare birth weights and gestational age to the model predictions. The other one, second one is to compare cancer data to the model predictions. we're also working on some projects with others to look at new private well data that has been collected and compare the new well data to what the models predict to see how well the models did or didn't do. And that will help hopefully in developing future models. And also those are national scale models, so they may not do particularly well in certain areas of the US. So it's just interesting to assess how well the models are doing. I'm also, since this was this workshop is about climate change, the USGS has started a new project this fiscal year to predict hydrologic drought, and I'm a part of that project. And I would like to include human health component within that project. So if you have, we're looking for stakeholders basically. If you have ideas of how we could combine some aspect of human health, and so hydrologic drought is not meteorologic drought. By hydrologic drought, I mean, you know, lower water levels in wells, lower stream flow, impacts to the hydrology. I'd be interested in talking about that. And then I'm also working on other models for other groundwater contaminants of concern. And in conclusion, so models certainly are not perfect, but they're useful to estimate concentrations, especially in unsampled areas. As we all know, sampling can be expensive and is not always possible to sample everywhere. I think the model results are useful in some of epidemiology studies, especially the ecologic studies looking at large scale human health data. And I really enjoy collaborating with epidemiologists. I think it's mutually beneficial. It's just really enjoyable to see the fruits of your efforts being used and applied in a meaningful way. So, and I will conclude with, I've had many collaborators, hopefully didn't forget anybody on here, and various funding sources from the CDC and within USGS. And that's it.
Great, thanks, Melissa. And again, for the sake of time, there was a question that came in through the chat. So I'll ask you that question and then we'll probably have to move on. And now I'm looking through and seeing if I can find the question, and there it is. And the question was actually from the next speaker, Dr. Janie Ingram. So perhaps she'll refer back to this in her talk as well. But she just asked the question of whether you could estimate the percentage of private well users that participated in the sampling. And I guess that means the percentage relative to the overall population of private well users throughout the country.
Yeah, so it's quite small. So it'd be, you know, 20,000 divided by, I think the rough estimate of total well users is around 14 million people in the US. So whatever that equals, 20,000 divided by 14 million.
And if anyone here wants to jump in having done the math, we would certainly love to have that.
I could do that.
No, just kidding. It's totally okay. Again, as I said after Lex's talk as well, Melissa will be involved in one of the breakout sessions, and then we'll all get back together again after that. So if you have burning questions or comments, save them for the breakout sessions, save them for the summary at the end. We'll have plenty of time to have that conversation very soon. And with that, thanks a lot, Melissa. I really appreciate you both attending the workshop and also your great talk. We really appreciate it.
Thank you.
With that, I'd like to introduce the third speaker within the triad of speakers today, Dr. Melissa Lombard, and Melissa will be talking about geospatial models of arsenic in private wells.
Alan, it's Janny.
Oh, I'm sorry. I don't have my glasses on. I'm sorry. How embarrassing. Did I get the name completely wrong? I probably skipped the line. Let me start all over again. Janny, I apologize. Our next speaker is Dr. Janny Ingram, and the title of her talk is Dissolved Uranium and Arsenic in Unregulated Groundwater Sources, Western Navajo Nation. Janny?
All right. Thank you. Yate she Janny Ingram Yeneshe Nanesteji Tachini Nishle Bilagana Bashish Chin Kinlachini Dashish Che Bilagana Dashish Nali. So that is for any one of my brothers and sisters who are from the Navajo Nation. It's great to be here. And thank you for the invitation to give a presentation. So I'm going to hopefully get this going. My computer's been very slow this morning, so I hope it moves forward without a problem. So I am going to be talking about actually work by the first author on this paper, Lindsay Jones, who's actually pictured there pumping some water out on Navajo. Lindsay got her master's with me through the Environmental Science and Policy program here at NAU. And there's also some work by former student Jonathan Credo, who's right now an MD PhD student at the University of Arizona. And then we collaborated with a geochemist, Rod Parnell, who has since retired from NAU. And so we're going to be talking, we've done quite a bit of work out on Navajo and water, but I'm going to focus this talk on the western region of Navajo. So, and just to sort of let you know, oops, I don't want to do that. Where I'm going to go with this talk. I'm going to give you a little background on why these issues are of interest on Navajo. I probably will not talk too much about health effects because Lex and Melissa did a great job on that. Give you some information about our study area. I'm a trained analytical chemist, so of course I have to talk about the methods. And then I'll jump into the results, and then how, which is really important in the work that we do, we provide these results back to the communities. So if you're not familiar with the Navajo Nation, it is a very rural area, about the size of West Virginia, although it looks nothing like West Virginia, as you can see from a couple of these pictures. But it's estimated that a bit over 30% of the homes out on Navajo don't have water infrastructure, so or power, so they're forced to haul from different water sites, and that's really been a lot of the focus of our work, is trying to help people understand the at least uranium, arsenic, and other elemental species in that water. So oftentimes unregulated wells are what are used just because they're closer to the homes out on Navajo. Unregulated just means that they're not tested. They're meant for livestock use. So they really aren't meant for people drinking the water, but people have been drinking the water. So that's where our work, I feel like, has helped people to understand maybe you shouldn't be hauling from this particular well. And then I'll talk a little bit more, but out on the Navajo Nation and the Colorado Plateau in general was one of the largest uranium reserves. So there was a lot of mining done in the mid-1900s out there. So this is a map of the Navajo Nation, and so it spans 3 states in the Four Corners area. So here's the Four Corners, here's Arizona, Utah, and New Mexico. And so what's shown here is the different regions of Navajo. They're called agencies. And so I'm going to focus a lot of the talk today on Western Agency or Western Navajo. The X's all show abandoned mine sites. So there is estimated to be over 500 AMU, stands for abandoned uranium mine sites. And then there were over 1,200 mine features, meaning that people, you know, attempted to mine those areas. And you can see a lot of the mining was in the western part of Navajo. So here's Flagstaff, where I'm located, and NAU is located. Up here, there's a community called Cameron, where there was a lot of open pit mining. And then the first mining actually is over here in the Four Corners area, in particular Cove, Arizona. There was underground mining there. We actually have a project going on up in that area. Then in the northern part of Arizona, Utah border, that's where Monument Valley is located. I've had a few students from up in this area. And then over here in New Mexico, in Eastern Agency, and my family is actually from about right here, but my grandmother's family is from the midst of these mine sites. So we do see, and I'll talk about this contamination of the groundwater from, we say from uranium mining, maybe it's from the naturally occurring uranium that is in that area. We've tried to do a little bit of isotope ratio work to kind of tease that out. It's been very difficult. And we also see that there's been increased arsenic and some movement of the arsenic, we believe, due to some of the mining activity. The maps that we saw in the previous talk had didn't have a lot of arsenic up here in this area. That's partly because this idea of a private well is kind of different than these livestock wells, because they're not supposed to be used for drinking water, but they are. So we've been trying to fill in the map to give that information to really, you know, give a better idea of really what the water quality is in those areas. So like I said, back in the mid 1900s, there was all this mining that was going out on Navajo. Lots of Navajo men actually worked as miners, were not given any personal protective gear. And so there was seen elevated levels of lung cancer and respiratory disease among the Navajo miners. The mining companies wanted to point at smoking. Turns out that Navajos really don't smoke that much. And so as a result, there was this Radiation Exposure Compensation Act of the 1990s. So some of the governmental federal programs and acts that oversee the uranium issues are shown here. So there's the Food Superfund and Comprehensive Environmental Response Compensation and Liability Act, or CERCLA, of 1980. And then there are two different uranium mill tailings kind of acts, the Radiation Control Act, UMTRCA, and then also the Uranium Mill Tailings Remediation Act, UMTRA, that were established. So there was acknowledgement that there were some issues with respect to the uranium mining that took place. Also in 2005, Dene, which is the way that Navajo say their name. So the Navajo Nation put forth the Natural Resources Protection Act, which actually used the Navajo fundamental laws to really build on protecting their own native lands. And in that, they said there was to be no more uranium mining. So we talked a little bit, or Melissa in particular talked quite a bit about some arsenic health effects, which you can show here. Arsenic definitely is a difficult player in a lot of different health issues, particularly if you have some sort of pre-existing issues. And then uranium we know is radioactive, so we know that's not good health-wise, can cause cancer, as was shown with the lung cancer in the Navajo miners. But also it really is a toxic metal, so it has chemical effects to the body. And so as you can see here, it really can impair the function of heart, liver, brain, kidneys, and it has been linked to cancer. So neither one are good at high levels. So Our study area, like I said, is Western Navajo. So you can just barely see it here is Flagstaff. And so what's shown on this map is, again, the abandoned mines are little X's, and they're mostly concentrated here in the Cameron area. Like I said, they did open pit mining. So if you're not familiar with that, you just take large bits of ore and it comes from the surface. And so as a result, I think it leaves a bigger mess than the underground mining because you have this whole open areas. The people in Cameron talk about some of the remediation just being throwing some of the mine tailings back on top to fill in those pits. So those are waste. And so they also put topsoil, brought in topsoil, put on top of the waste, but didn't revegetate. This is a super arid area, so that soil just blew around. So they're still working through any type of remediation in this area. But you can see that we looked at number of wells all through the Western Agency. So the black dots are all the unregulated wells that Lindsay Jones sampled multiple times for her project. So in all, she tested 82 wells. And again, these are wells that are called unregulated because they are livestock wells for the most part. And so they're not really meant for human consumption. So a little bit of geology. So the water, the depth of the wells varies, as you might imagine. But this just shows all the different geologic formations in the Cameron area in particular. And so you can see, sort of how deep you go into for the well depth, it will make a difference as to, where that groundwater is in the overall picture of things. Watch my watch. And so this is just another look at, did I change the thing? This looks about the same. This is just a bigger look. We have different aquifers that are being drawn from for Western Agency. And so I think my next slide actually shows, let's see, I'm struggling with, like I said, this is really slow. So what Lindsay did was to make two maps the different wells that she looked at. What she did was to see where in that geologic depth, what were the different wells, how deep were they and what different formations did they go through. So you can see there is differences among the different wells that we looked at. And then this is showing the depth of the well. So you can see some of them we don't know. It's very difficult. I had a student, he's now Dr. Tommy Rock, who spent a lot of time in the capital of Navajo Nation, Window Rock, trying to get information on the depths of these wells. A lot of them were, dug, I guess you might say, back in the 40s and by the Indian Health Services, so trying to find that information. But for the most part, you can see there's some shallow wells, which are yellow, and then the green ones go from 100 to about 250 feet. And there are some deep ones, but they are mostly up in this northern region of Navajo Nation. All right, so in her thesis research, Lindsay was trying to answer the question if there were spatial variability among those unregulated water sources in Western Navajo Nation. She also actually looked at some temporal information from some old data that our group had collected in the early 2000s, as well as trying to get other existing information, such as some of the data that was provided by the Army Corps of Engineers from the late 1990s. But I don't think I have enough time to talk all about that. So I'm just going to talk about the spatial information. So she was interested in, what the natural influences, such as, the seasonal recharge, and then just depths of wells and those kinds of things. We were very interested in the anthropologic influences. So of course, past mining, but like I said, it's because that area had good uranium reserves, it's kind of hard to know if the mining made it worse, you know, if that impacted, because there's very little data from prior to any mining activity out there. And then just kind of looking at overall water quality. So she did more than just uranium and arsenic for her thesis to, you know, try and get a bigger picture of the water chemistry. So, you know, what we were really interested in is, you know, is there some human health risk in these wells? And if so, then trying to give that information back to the Navajo people and really trying to understand, you know, some of the hydrogeologic issues that, you know, determine the different concentrations that we were seeing, in particular of uranium and arsenic. So if you haven't worked on tribal lands, these are sovereign nations, which means that they have their own governments, and it's imperative, not just important, but it's critical that you get permission to be able to do these studies. And so this is a picture of Lindsay presenting at the Western Agency meeting. So the Western Agency is that whole region that she looked at. She also got resolutions of support from various chapters to be able to show to the larger Western Agency that people were in support of this work. You know, by and far, people were very supportive because people are very interested in their water quality out on Navajo. And so what I'm showing here on this side of the slide is just that resolution of support. So you have pretty much documentation that you have approval to do this work. So out in the field, collection of samples, you know, definitely got the location of the wells using GPS, and then went through pretty much EPA methods to do the sampling, collection, storage, and so forth. And then collected some data out in the field, oxidation reduction potentials, pH, you know, those types of things, some conductivity of the water. Like I said, in general, Lindsay was trying to get some overall water chemistry. So you can see a few pictures of different types of wells. I'm going to show a couple more pictures at the end. So bringing those samples back to the lab, then to do the uranium and arsenic analysis, we used inductively coupled plasma mass spec. And then she also analyzed for major cations, sodium, potassium, calcium, and magnesium by flame atomic absorption. And then we sent sample down to the University of Arizona's Arizona Laboratory of Emerging Contaminants, the ALEC lab, and they did major anions for us. So this is really the data that I want to show you. What you're looking at on the on the y-axis is concentration in part per billion or micrograms per liter. And both arsenic and uranium are shown on these plots. The data shown in this plot to the left are the data that Lindsay collected during her thesis work. So April, May, July, September, October, and December of 2018. And then we show the drinking water standard just to give you an understanding of, you know, sort of what is elevated over what one would expect if you were drinking this water. So the orange is arsenic, the blue is uranium. So you can see arsenic, as was stated earlier, in this country is 10 part per billion. Uranium is 30 part per billion. So you can see this is the total number of wells that she looked at. So you can see quite a few of them for arsenic are below, but there are some in this 10 to 30 range, and then there's a few that are a bit over that. We certainly don't see the levels that you saw in the Bangladesh study with Lex, but they are definitely elevated to some extent. And then we see uranium, again, below that 30 part per billion threshold, but definitely some above. Okay, now in this plot on the right side, she has superimposed data that was collected by my lab early in my time here at NAU. I came to NAU in 2002. And so we started to work out in Western Navajo by the request of the community. And so again, you can see the 10 part per billion line for arsenic drinking water standard, and then 30 for uranium. And again, you see some elevated levels of arsenic, actually seems to be more than, more recently. So that was where the temporal work that we wanted to try and do. But I'll talk about the limitations of doing that out on Navajo a little bit in a few slides. But anyway, you can see we also have in 2008 another set of data, but this is only uranium. We were having struggles with our arsenic analyses, and then we started to pick back up with arsenic and uranium. And you can see, there are some elevated levels. In a different paper that I'm not going to talk about, that was first authored by Jonathan Credo, we actually provide by chapter, which is the different communities, information on the number of wells in those chapters that have elevated levels of uranium and arsenic and some other elements actually. And so that is actually for a lot more of the Navajo Nation. And I think that also kind of helps to give that sort of perspective on some of the issues out there. So what Lindsay decided to do was to make this uranium risk map and arsenic risk map for her study area. And so what you're seeing is concentrations of the number of wells, and then sort of going for very small, the little yellow dots, below 2 part per billion, all the way up to really high levels here. And so the map I showed you, or the data I showed you previously here, we actually took those really high levels off because there's not a lot of those wells, but there are some, but it would just squish down our scale. So there are some very high levels of uranium in some of these areas, particularly in the mining area, as you can see. There's one outlier up here in Lichi chapter. Same thing with arsenic, and you can see there seems to be overlap. So coexistence of high levels of uranium, high levels of arsenic in similar regions. This coal mine area definitely has issues of higher levels. And so it was, I think very useful to kind of spatially see what we're doing. We're not really geospatial folks, but we have been working more with some folks from the University of New Mexico and Montana State buildings that have those capabilities and really understanding that information. So one of the things that Lindsay did that I thought was just really great and turned out to be very helpful to folks on Navajo was to put together like a booklet where she reported the information that she collected by chapter. And what she did was, so this is the front of the booklet, but these are like 2 facing pages in the booklet. One page had the chapter itself, so the map of this chapter, along with the specific wells that she analyzed. And this became very useful because oftentimes the Navajo government may refer to a well as 5T-529, but the family might call it Auntie, Margaret's well. So it's sometimes difficult that we're not on the, we're talking about the same well, but we don't know it kind of thing. And so having this map was really useful. And then what she did was summarize the information and provided both the uranium and arsenic data along with that drinking water standard dotted line. And the idea was that we wanted to be able to just say, not so much teach them about concentrations and so forth, but just to say if these bars are above those lines, then this is not good, and you want to, it's above what the EPA decided was the drinking water level standard, and so you want to not use those wells for your household use. So she did this for all of the different chapters, and then what she also did was she attended the chapter monthly meetings at many of the chapters, handed out the booklets described the booklets, described what the folks were looking at, took, questions. She also talked to grazing officials, because it's really important for people who are grazing their livestock out there, as well as the Western Agency larger meeting. And then we actually made 1,000 booklets, but it turned out that more people were interested, so we copied more, and we would leave them with the chapter officials for people when they came to the chapter house to get that information. So the recommendations really were that, people should be aware of at least the uranium, the arsenic. There's other issues with some of the water out there, but when they're using it for their household use, signage is really important. Back in the 2000s, the University of New Mexico, led by Johnny Lewis's group, had put signs out about, levels that were not meant for human drinking water, whether they were high in arsenic or uranium, and we just felt like that was something that people should heed. Sometimes people would take those signs down, which is kind of, defeats the purpose. Like I said, she presented at many, many different chapters. What we found over time, in particular, Tuba City in Western Agency is probably the largest chapter, and the grazing official there has became kind of a friend of Lindsay's. He's seated right here behind her, and he actually helped connect her to other people within that region and helped her to find different wells and which wells were of concern and so forth. So as she put, this is her slide, collaboration was very, very important. So some of the things to consider, these are different pictures of the wells that are out in Western Navajo, and really they look similar to those that are all across the Navajo Nation. And so trying to do this comparison of water levels over time became very difficult, because as you can see, a lot of them are these open tanks. And so depending on, time of year and heat and evaporation and so forth, those levels are going to change, but not so much water quality as this water that you're being pumped up, but part of it is because it is sort of left out in the environment type of thing. There's just a whole variety of types of wells. There's hand pumps, there's a lot of windmills out on Navajo that pump that water up. Like I said, these holding tanks, some of them are just sort of drip sites, and you have to, this is what's trying to be shown here, you take a beaker and dump it down into the well to scoop out the water, and then there's definitely these livestock troughs that are used by people that own livestock out there. So there's just quite a few different kinds. And then you can see here, there's Rabbit Bush Well, so that's one name of the well. There's 39 PHS-12. So it just, the names of the wells also we found to be interesting. Some of them we didn't even know what the name was, and so the students would name the well something that was sort of unique to that particular well, but having that GPS location was extremely important. So the reason for doing this work is because the Navajo people still to this day rely on hauling water. And the cost of hauling water compared to turning it on in my tap in Flagstaff there's just a huge difference in cost. And so it's really important, even though maybe there's a well very close by, knowing what the levels of uranium, arsenic, any other things that could be of interest is really important to these folks. And so trying to get that information, not just to them, but also to tribal officials. So a side little story with the pandemic of COVID, it hit Navajo really hard. And we were told by public health to wash your hands, wash your hands, wash your hands. Well, if you don't have water in the house, that makes it very difficult. And then there was a lot of lockdowns out there. And so that was another thing that was very difficult, because people weren't allowed to drive to the nearest regulated site. So really we're depending again more on the unregulated wells. And so we had previously been working with University of New Mexico to sort of marry our database sets of water quality information. They had done much more on the eastern side of Navajo, us on the western side. And it turned out that, you know, we had started that work about 3 years ago. It turned out it was really important for the tribe to have that information so they could give that to the Navajo Nation. And Joe Hoover, who's now at Montana State Billings, and some of his colleagues have a really nice data set, Navajo Safe Water, where people can go to look at that and try and find that information. So, you know, the importance became even bigger in the past year or so. So we through the work that Lindsay's done, you know, we have gained insights on water quality from water coming from the different aquifers. And I think we have built more trust among the research team here at NAU and our Navajo community members. We have been asked to look at other water, and so we you know, have been doing this since I came to NAU, and I'm assuming we'll continue to do this. So like I said, we really want to understand this long-term temporal changes, whether it's drought, whether it's, you know, usage, because they're drawing from these aquifers differently, you know, what might be changing these things. But it is a challenge. Those are challenging samples to collect, kind of thing. And really, this bottom point, we're working on a manuscript right now to, you know, try and kind of present our lessons learned on how you disseminate this information back to the public, and in particular to communities like on Navajo. So with that, I'd like to thank my lab group, who is awesome at going out and helping with sampling. These are the people that were on Lindsay's committee, definitely the local Navajo government and community members and the ranchers, and funding from the National Institute of Environmental Health Sciences. So with that, I can take any questions.
Thanks, Jenny. For the sake of time, we're going to move on. And we've just cut in a little bit into our 5-minute break period. So we're going to take a break right now, and let's come back at 10:47. I have 10:41 right now, so we'll come back at 10:47, and it looks like people are still populating the return from the breakout sessions, but welcome back, everyone. And as per our usual protocol, we're now going to ask for the breakout session coordinators to talk about what was discussed in their breakout session. So Kathy, you happen to be at the top of my panel here of top of the list of panel members here. So why don't you go ahead and begin?
Okay, so I will start. We had a very interesting conversation and several points came up. The first really was brought up by Ellie, who mentioned that we really could use to involve citizen scientists more in this process, but we do also need to make sure that we understand the parameters around the measures that we can get out of things like those kits. And again, scale is pretty important. And so Lex brought up, right, with arsenic, you have a scale of multi-folds levels that we know are there. And there's like low levels we know maybe aren't so problematic, middle levels may be problematic, and then high levels we know. And Crystal brought up maybe using a red, yellow, green format for communicating those risks is important. For things like fluoride, though, it's a much narrower set of risks. You need a little bit for good health, and it's a little bit less of a, it's a more of a health problem at higher risks. So those kits maybe need to be a little more accurate in their measurement quality. We also kind of came back to risk communication and how do we put forward risk to the general public. And that's something that Crystal has a lot of experience with. So I'm going to throw that over to Crystal Powers and let her talk a little bit more about some of the things that they've been doing to figure out ways to communicate risk. So Crystal, if you're here, maybe pop up.
Sure. I won't spend too much time. I can always follow up with questions, but basically my shout out is to that there's a whole field of research in communication science and risk communication science, and to make sure we're working closely with professionals in that sphere. Some of what we've done, just to really quickly talk about it, was to make sure that we're using a broad set of stakeholders and engaging them from the beginning, so they feel like they have buy-in to the process. And so that all came around to a lot of buy-in to creating a more robust communications campaign around specifically nitrate. And we're just kind of getting into the phase where we're talking about, well, how do we develop these I mean, I've been part of a water website that's done some communication of this, but we're hoping to kind of elevate it to the next level. So glad to take questions or talk offline about it.
Great, thanks. And let me just remind everyone that we have about 40 minutes before the end of the session today. So there'll be plenty of time for group conversation once we get past the check-in with the breakout groups. So Jesse, why don't you take a shot at letting us know what you discussed in your breakout session?
Sure. I think we had a really nice discussion, and one of the first things that we talked about was scale and the scale of the 3 different projects and how they were, there was some overlap, but there was also some difference between the 3 of those, and how that was kind of a central theme for today, whether looking at a smaller scale or a more national scale or also temporal scale to some extent. I'll get to that in just a little bit. Machine learning was a big part of our discussion. And it was brought up by Brett that it was really nice to see that there's more of these types of techniques that are being used and deployed into these types of to studies. I think Jennifer mentioned that it's the who and when of moving to more of these types of modeling efforts with contaminant transport as we move forward to try to figure out where more of these opportunities are going to come up and how do we potentially take better advantage of those opportunities as well. And that's where Melissa's work is really interesting, because when you look at machine learning as a whole, it can be easy to implement, which means that anybody can grab things and try to plug and play and see if they can get it to work out, but it doesn't necessarily mean that you're using it correctly. And one of the things that Melissa talked about was they had kind of almost a community of practice that was based around machine learning, where there was experts throughout the country that worked for USGS, I believe, that were working on machine learning so that they could come together, because we have the technology now that we can easily share when we're trying to do these more complex methodologies that we don't need to be right next door to somebody. And so that provides a unique opportunity so that we can be more careful with our studies moving forward, but also be more collaborative and broad scale collaborative as well. And then Brett brought up that forecasting. I think it was Brett. I might have misquoted on that one, but Brett definitely talked about it to some extent. Jennifer might have as well. Forecasting and being able to forecast some of the risk associated with this as well. Can we actually better identify where is some of the potential risk associated with this, and with contaminants and with contaminant transport and within the environment? And there's multiple scales there that we could potentially look at. We can look at seasonality, we can look at short-term, few years, or we can even look long-term, similar to what some of the climate change work is doing. And with that, looking at some of this, that's where we could really benefit from collaborative research with other groups and other disciplines that have already been working on this, similar to climate weather, meteorology. Brett, feel free, or Jennifer, feel free to jump in if I messed up or said anything incorrectly there. And then Alex brought up some really good points about going back to how do we actually get more engagement down at the ground level? And schools and children really seems to be a central theme to this, and finding opportunities to try to better integrate through either citizen science or school-based projects to make sure that we're doing more on the ground level. And we had a nice discussion about, because Alex is from Mexico, so we had a nice discussion about, is it even possible to do something like that across the United States, where you have school children across all of the US to be able to do these types of projects, which there's a number of barriers that potentially here or internationally with doing those types of projects. And one of the things that came up is issues associated with regulations. And sometimes, you know, policymakers and certain individuals might not want to always see these issues and would prefer if people didn't bring attention to them. And so that becomes an obstacle that we have to try to address in trying to deal with some of these very large scale issues. And I think somewhere around there, that's when we got shut off. So we had to come back. But it was a really nice discussion, and wish we could keep it going for even a little bit longer.
Well, you actually can, because we have 35 minutes left, and perhaps we'll loop back around to that. In our group, we had our group. I think it's accurate to say that our group got a little bit further down into the weeds, where we were talking about. Dr. Ingram was in our group, and we were talking about both the Navajo Nation and some of the specific issues. And then also Dr. Ray was in our group as well. And I'm going to open this up to both either Chitarandran or Dan Snow. And perhaps they can talk a little bit more about their Know Their Well program, which I believe a link has gone out to everyone relative to that. And I know that came up yesterday as well, but perhaps we can talk about that for a moment. The other thing that came up was the issue that was also touched upon yesterday, was that there are situations where individuals will allow access to sample either surface water or groundwater, but they don't want to know. They don't want to know the answer to the question. They don't want to see their real estate value go down. They don't want to. They don't want that information back. And it kind of gets to the socio-political environment that we currently live in. And if one of the points is betterment of the community, how do you deal with the fact that there are perhaps large subsets of individuals out there that don't really value what the data are saying? So with that said, and relative to anything that was said from among these three breakout sessions and the summaries that Kathy and Jesse and I just gave, who would like to initiate some conversation?
I can jump in, give a little bit historical perspective of what we did. Basically, it started from Illinois. Soon after the EPA's pesticide survey was done around that time. It was published in early 90s. So Illinois also has a lot of, as you saw this morning, the USGS map, a lot of domestic wells. So they did a pilot study, the two surveys, Illinois Geological Survey and Water Survey. That time I was a student at the U of I with the Illinois Water Survey I was working. So this involved primarily rural areas, but a lot of in-person interviews and getting the township size areas in 5 counties. So first getting to know the people, they're interested or not, local advertising, newspapers, radios and all that. Then finally, we selected about 64, 65 people for final interview and picked 48 from each of those township size areas. And it went through a long elaboration of 2 hours or so interview, getting to know the well site information to land use to all the details. So that pilot co-op study 14 or 15, I had shared that link. Actually, it's published in the 90s at the Illinois. Then that time also we started using the machine learning language, or we used to call neural network, how to use this information and do some predictive runs. So those things were published in early 2000. Then before leaving Illinois, I initiated this FFA project there, but moved to Hawaii. There was not much to do there at the FFAs. So after coming to Nebraska in 2013, we started this project with the Nebraska Environmental Trust funding. So that funded about $400K to do this study with 15 or 16 high schools. But instead of manually getting that data, we developed an app with the computer science faculty to capture what are the well site specific or land use or other cultural practices that might be contributing to well contamination. That's what the students really, the intent was, it's not a citizen science, it's a learning exercise. So once the students do their own analysis and our lab provides them the QA/QC or quality control data, so then they will have to go back and check what information they got from their site surveys and why one site is having more contamination versus the other site. Did they have animals in the past? Is their well located in a depression or in a hill slope, or is too close to the farmland? So those kinds of information. Do they have surface sealing or likely entry of surface water into the wells? So those types of things. So that basically took off. We are finishing the phase 2 now, trying to go to phase 3 of this Know Your Well. And Dan is also trying to work with our other faculties to get NSF fund, maybe another project looking into both involving the high school teachers as well as students through formal and informal education program. So I think I can stop there and let Dan jump in if he has to add anything.
Dan, would you like to add anything to that?
Maybe phase 3, Dan, maybe a little bit. Maybe he's out. So phase 3 is going to involve maybe 8 or 9 NRDs, a bunch of more schools and gradual funding from the Nebraska NDE, Department of Environment and Energy, and other sources of funding. And we just want to expand that. There is a lot of interest actually. Jesse probably knows that the kids from the 5 schools in that area who are involved right now, they got a standing ovation in the conference, and Kearney also same thing. So this is the way to involve the school kids. I think that's going to get a lot of traction.
So I have a question for the group, and that is looking at or discussing what Lex mentioned earlier on this morning in the first talk, and dovetailing that with what Dr. Ray was just talking about. And then I'd also just like to call out that Ella Santana Bendix is one of the panel conversants right now from I'm sorry, I believe it's Costa Rica. Isn't that correct? And my question is, taking the idea of what could we, and I don't think we're going to answer this in 20 minutes, but is there a value to take what has been discussed today, either from a citizen science or a community-based participatory research type of approach, and take that to developing countries such as Costa Rica, where there are very clearly, from our breakout session, very clear water quality issues that can adversely impact human health. Is there a way that we can effectively generate some sort of a methodological toolbox, if you will? Maybe that's not infrastructural hardware, maybe it's more conceptual, but does that have any traction, or does that have any value?
So, is it targeting the second-tier economic countries or real drought poor countries, or which ones you are looking at?
Let's open up to the conversation of whichever one you would like to talk about.
Maybe you can do in second-tier countries like Costa Rica, but you look at the real bottom, really the bottom 50 or so. I think it might not be, but who is going to test their water actually? Who is going to bring the funding? So that is a thing. Maybe I'll leave it to Lex to address that, who has done a lot more in Bank.
And
Just
I'll,
about
one little piece of context that I might throw in, it also comes back to your point about when people don't want to know the answer. Because I think another motivation for that is if they don't feel that they have the ability to do something to remedy it, they don't want the fear of knowing what the answer is. And so particularly when you start to talk about going to, I mean, that's an issue even here in the US, let alone when you go to other countries, if you aren't pairing the data with some way to remedy, I would say you may not get the results you want.
I agree with what you just said. What I also think, though, is more often than not, the people don't realize that there are options around them, that are not expensive. And so I think somehow the testing has to be coupled with that and very much tailored to the local situation. Going back to maybe the initial point, I think what's revolutionizing our field in this sense is smartphones. In the area where I've been working for 20 years, not every family had a basic phone at the time, a mobile phone. By now, just about every family has at least one smartphone. Always, usually it's the younger generation in that family who owns a smartphone. I mean, that's I think the key for mapping, for conveying information, for advertising services. I think that would be the thing to build on.
Kathy, you had some ideas earlier on that you were sneaking to me in the chat. So do you have anything you'd like to add to this conversation?
Well, one thing, and I think we'll address this more tomorrow, but to bring the conversation back to the title of the whole workshop series is, where do we have an intersection between climate change and this issue of chemical toxicants? And I guess the second topic that we got into in our, so I guess these are desperate or different questions. So I'll stop there and then maybe come back to my second comment if we get any conversation going on this first topic. Because really that's why we developed this, is we see these two big crises coming down of chemical toxicants in water systems as just one place. But how does that water system issue with chemical toxicity and toxicants intersect with climate change? And maybe I'll just throw that out there as, please think about it and bring it back tomorrow at our final meeting together. Or does it not?
And if I could just add one thing is, as we look into the future, we're much more familiar with conversations around climate change, but what are some of the other global changes that are going to occur that might also impact, chemical emissions or bioavailability or all of these processes?
Thank you, Brett. Another issue, and I think it's really, we've been bringing it up, is how do you communicate the risk? And what do you do when you have individuals? I have individuals come to me all the time and say, what is my risk from the well water that we have that has 3 ppb of arsenic in it? How do we communicate that risk both to individuals and to the general population? And as scientists, we can often be a little wishy-washy on how we communicate the risk, because that risk at something like 3 ppb is a bit wishy-washy, right? So, and the general public doesn't like a wishy-washy answer. They want you to tell them, this is a problem. The folks want me to say, you get a mouthful of wastewater created snow and you're gonna have a health issue. Well, I can't say that, and people don't like that answer, right? So how do you communicate the risk in a way that's appropriate and doesn't either scare people on one side or make them underestimate risk on the other side?
That's a really interesting question. And I think it dovetails pretty nicely both with the conversations that we were having yesterday about that. And also the conversation that, or the talk that Lex gave this morning when he was talking about taking his the arsenic data and binning it, putting it in different bins. Because again, as we were talking about yesterday, relative to the utility of certain type of strip testing or community-based testing, the community doesn't care whether the arsenic is 57 or 58. The community cares about whether it's 0, if the community cares at all. The community cares about whether it's 0 or whether it's 100, whether it's going to hurt myself or my children or my livestock, or isn't it? I mean, those are the kind of issues that we're dealing with. So in a way, it's almost like lesser is more, right? Less information, or maybe a more discreetly binned information is more powerful.
So I just wanted to jump in on, I worked with a team who looked at a big mine spill that happened in Colorado that then came down and affected the Navajo Nation. Anyway, trying to provide that information back was definitely I'd say the biggest challenge. And there were some other challenges with that project, but essentially, I think wrongly, our team tried to sort of educate in all these scientific, what is a part per million? What is a part per billion? What is the regulatory level for livestock, for fish, and all this kind of stuff. And I mean, these were like many PowerPoint level community talks. And, the grandmas were like, is it safe or not? That's, and they would come away so frustrated. And I know, like, we just were almost afraid to say it's safe or it's not safe. And so I agree with Kathy. We as scientists got to figure out how to provide those findings back where people can use them and they feel like they understand and they're not, overwhelmed or confused or like, what are you even doing kind of thing. So it's very difficult because I know it's hard no one wants to say, safe. It's just drink the water. It's good, that type of thing. But we have to figure that out.
Well, and I think there's lots of other people working on this issue because it's very common in health, even with something like your blood pressure, which we all should know our numbers. But there again, there's kind of red, yellow, green. And so I think there's a whole field in health communication that like I said, I keep coming back to it. But I'm like, we need to get those people involved in the, so our role is to figure out what are maybe the bins, and then we work with some of the communications folks on how to communicate that in an effective way.
So, Alan brought up creating a toolbox. And I think within that toolbox, there's 2 other things that can go in there besides the usual scientific methodologies for citizen science and or CBPR-like research. And that is a communication tool for how do you communicate both at the beginning and at the middle and at the end of any project, as well as how do we pull in the fixes so that you don't start without communicating, here's what we'll do if we find a problem. And that needs to be built into whatever kind of toolbox is developed to do the kind of research that we're talking about at a broader scientific or citizen level. I'll be quiet. Gabe, you unmuted, so I'd like Gabe to come in.
Gabe, we're still having trouble hearing you. Well, Gabe, are you on?
In the chat, he says, go on and I will figure that out.
Okay. While we're waiting for that, one thing that struck me in this most recent conversation relative to communication is the, for lack of a better term, and I'm not trying to get political here, but the other side has communication really well down. And relative to relative to emerging contaminants and endocrine disruption, it's one terminology or one phraseology or one lexicon that's used is that chemical is in is at the equivalent of a shot glass in a swimming pool. And that has there's a lot of nuance to that phrase, shot glass in a swimming pool, because it harkens a lot of images, and it kind of denigrates the concentration without coming out and saying so. So the other side is sometimes really, really good with their capacity for lexicon and their capacity to minimize the risk or the importance through their communication skills. And as Kathy was just saying, for many of us, we don't have that proficiency perhaps with the language in order to come up with those phraseologies that just stick in people's minds to make them recognize that perhaps an issue is an issue, or that it's there's more to it than what they initially think.
Well, I'll put a plug in for, so my background comes from some work in climate science communication and following the research that's been done there. And, you know, there were definitely mistakes made, but if we learn from the research that's been done on that, I think we know a lot more about how to do a good job with that.
Mm-hmm. Lex, go ahead.
I have a little anecdote that I don't think is just specific to Bangladesh and builds on what Gabe wrote in the chat. You know, this idea of the traffic light signal. So when we started testing wells, that's what we wanted to do too. But we had a problem, which is that the government standard was 50 ppb, WHO guideline 10 ppb. We wanted to give both pieces of information. At first, we thought, let's use green, yellow, and red. But the government people with whom we want to continue, you know, to collaborate, of course, told us, but yellow is not consistent with this country's regulation. You're giving an incompatible message. And so that's why we switched to blue, green, and red. And I think that may happen, you know, on other, you know, concerning other contaminants. Maybe a regulation is not sufficient and you want to convey that. And so there will be a bit of tension occasionally to overcome.
And I think we also have to take into consideration the cultural differences in communication, along with things like, what does the government really want us to put out there? But building in some of those, the flexibility in how you communicate culturally appropriately is also going to be very important in trying to come up. There's not going to be a tool that fits everything, but there may be basic aspects of that tool that we can then adjust for being culturally appropriate.
And I think it's interesting that we're having these conversations, and now in both days, yesterday and today, the conversation has gone from being from the speaker's information, which was fairly technical and fairly scientific and totally germane to our conversation. And it's in both days, it's kind of boiled down to science communication and trust with the affected communities. And I just think that's really interesting. And I also think it's quite refreshing that a bunch of scientists and allied scientists can get together and get to that point where perhaps 20 years ago, that may not have been as common. So I think there's two other things here. One is I don't think we need to belabor the point here, and that is, I don't think we all need to sit here and look at each other if there's nothing left to say for 12 minutes in order to satisfy the time. So I'm going to put that out there first. But the second thing, and I did this in the breakout yesterday, is there's a number of students on right now. So I would be interested to hear either from a student or postdoc, a young professional's perspective of what they've heard today. Anybody brave enough to volunteer for that? Apparently not. Well, unless anyone has any other, Elizabeth just lit up. Elizabeth, would you like to say something?
I will. And I should probably start by saying Dr. Kolak is my advisor. I'm at the I'm at the University of Idaho. I'm a first year graduate student. But yeah, I really enjoyed today's workshop, and I really like the kind of common theme of collaboration and communication, not just among scientists and across disciplines, but also with communities too. So, and that's something that I'm trying to do with my research. So it was really good to hear professionals speak up and kind of talk about their experience in an actual out of academic type of atmosphere. So yeah, thank you.
Does anyone else have anything that they would like to add before we perhaps adjourn until tomorrow?
Alan, you mentioned about the climate change angle, and these days in the last 5 years or so, I would say that the health effects of cyanotoxins, that's becoming a little bit more of an issue. How much that bloom is connected with the temperature, probably one. And the runoff part, I don't know whether you can have a little connection with heavy precipitation, more runoff or more losses of the nutrients getting into lakes or surface water bodies. And I'm not sure, we are probably studying this to depth in this country because of the Toledo other issues, but what the situation in developing countries, which are already experiencing very high temperature change. And many rely on the ponds or other sources for drinking water. So I'll stop here. So maybe there's something to think about that.
Jesse, in your, I'm going to pick on you since you're the climate guy here relative to the conversation tomorrow. Would you like to respond to that and the interplay perhaps between climate change and toxic algal blooms?
Yeah, I mean, well, you know, it's such a complex issue, and I'm not going to pretend that I'm an expert in this by any means. So if anybody else has information, please feel free to jump in. But with the harmful algal blooms, you know, you have changes in precipitation, which then can lead to the formation of some of these algal blooms, both with nutrient loading that could occur, but then also drought conditions, which then can cause for more stagnant water conditions. And then along with that, temperature related issues as well, which we're experiencing that all across the United States. You know, right now in the western part of the United States, we're in a massive drought, or slowly moving towards a massive drought. So, but yeah, I mean, I think that, and this is what I'm going to talk a little bit about tomorrow as well, is just some of the complexity around some of these issues when you throw in climate change all of a sudden on top of it. Climate change is like this overwhelming issue that we're constantly facing. You know, our Earth's climate is changing, and then the context, we're also changing our exposure to environmental contaminants, our population is growing. Kind of going back to what Brett said, we're having a convergence of a lot of different issues simultaneously happening at the same time. And I'm not really sure what this is going to look like. It's a big untested experiment that we're trying to move into. And so with that, you know, and you go back to what Melissa talked about today with potential exposure, more exposure to arsenic with drought conditions. And we know that the western part of the United States is getting drier. But we also know that the intensity of droughts are increasing as well. So that's just one example, but we're not looking at it in the context of other contaminants. that we probably should be trying to put some focus on as well, with what does this actually mean as far as, let's just say, private wells, if all of a sudden droughts happen or flooding happens, and what does that potentially mean for water quality issues that we're going to see across the United States. Yeah, it's, you know, we have to be prepared for the unexpected, I think, moving forward. We're not even really prepared for what we're experiencing now, so.
And then maybe one other thing to bring up for tomorrow as a discussion is, could there be indirect effects as well? So for example, climate change affects fish populations that then influence food security in some parts of the world, right? So that it's not just a straightforward link and intersection. There's a lot of indirect potential effects as well. Heat stress is one kind of stress, and chemical stressors and exposure to toxicants is a different stressor. And there may be very different responses under different environmental, the intersection between those stressors that aren't necessarily thought of as direct combinations of the two factors.
I think that's an excellent point. You know, the first one I think of, it doesn't necessarily, it's not this, but I think there's a parallel. A lot of psychiatric drugs, or some psychiatric drugs with exposure to heat, they become either less effective or more effective, and are not more effective, but have less control, allow for less control. And so, which then can lead to episodes and mental and behavioral health issues that can potentially arise. And so I think, yeah, and Mary Hayden, with her presentation, or with one of the discussions that we had yesterday, talked about that to some extent. It's really difficult to look at all these confounding issues that could potentially be linked back to, you know, it's not just nitrates. It might be nitrate, or it might not nitrate, but nitrate and atrazine, nitrate and other potential contaminants, uranium, et cetera, et cetera. But it also might be nitrate and drought with concentrations of that we see in our water systems. So, and then you throw on all of a sudden other potential changes on top of that. Who knows what the outcomes could be.
Jesse, one thought that carbamazepine being the signature chemical right now in the wastewater, that's for epileptic drugs. It might be interesting to look into the temperate climates where the wastewater is discharged to rivers or lakes versus southern states where we have much more warmer temperature. What happens to the fate of that carbamazepine going into a southern lake versus a northern colder lake or something like that?
I agree. And I think that's the importance of doing a lot of these studies, and for regionally specific studies around some of these issues, because of the complexity of the problems that we face. The first thing I think of is West Nile. I remember a study, you know, in Nebraska, drought and precipitation is strongly correlated with West Nile, but other places in the United States it's not. And it's just because there's regional specific issues associated with it. With the emergence of that pathogen, which is the exact same thing with potentially with some of these chemical contaminants as well. There might be regionally specific linkages that we need to better understand, especially in the context of climate.
And with that, we're pretty much at the bewitching hour right now. And with that, I think the conversation of the last 10, 15 minutes is a perfect segue into Jesse's session tomorrow relative to climate change. Remember that although we did lose one of our speakers to an unexpected illness, we will start at the same time. So that'll be noon Eastern, 9 a.m. Pacific. And I'd like to thank you all again for the great speakers today, as well as the great conversation, both in the breakout rooms and in the collective room together. So with that, thanks everyone, and we will see you all tomorrow.